It's a pleasure to introduce Guillaume Rond, and he is a professor at the Université de Marseille in France. Today, Guillaume will talk about semialgebraic and the subanalytic sets. Thank you, Guillaume, and you can begin whenever you're ready.
Thank you for the invitation here. Yes, I will talk about semi-analytic locus of a subanalytic set. So my interest here is to study the structure of the image of real analytic sets under analytic maps. So we'll start by recall the situation in the algebraic case. And I mentioned that this is the joint work with André Bellotto and Octave Curmi. So I start with polynomial maps in the complex case. So we have the Chevalier theorem that says that if you consider a polynomial map and an algebraic subset of Cn, then its image under this polynomial map is a constructible set. So a constructible set is just a set of this form. It's a finite union of sets defined as the vanishing locus and non-vanishing locus of polynomials. So here, the P1, PL, and Q are polynomials. In particular, because the image of X is constructible, it's not too wild. So, for instance, constructible subsets of Cn is very close to be algebraic, in the sense that if we consider the smallest algebraic set containing a constructible subset of Cn, it has the same dimension. So this is the remark here. F of X is a constructible subset of Cn, and so it's Zariski closure, which is denoted F of X with a bar over F of X. It means that it's the smallest algebraic set containing F of X. And the dimension of this Zariski closure is the same as the dimension of F of X. And it's less than the dimension of X in general, okay? So this is a situation for algebraic maps, polynomial maps, over a complex, the field of complex number, or over an algebraically closed field in general, even in positive characteristic case. In the real case, we have the analog of Chevalier theorem, which is usually called the Tarski-Seidenberg theorem. And it says that if you consider a polynomial map in the real case, then the image of an algebraic set is a semi-algebraic subset of Rn. So a semi-algebraic subset is not exactly constructible subset of Rn, but it's defined like this. It's a finite union of sets defined as follow. So it's the set by a set defined as the vanishing locus of some polynomials, and the fact that some polynomials are positive. Or if you take minus Q1 of the Qi, the polynomial is negative. Okay, so it's a bit different, but not that different from the complex case. We still have this fact. It's a semi-algebraic set. Its Zariski closure has the same dimension as the semi-algebraic set itself. And so in particular, the dimension of the image of X, its Zariski closure is less than the dimension of X. Is it okay? If you have any question, do not hesitate to ask me, okay? Okay, but in this talk, I'm interested in not polynomial maps, but analytic maps. So in the analytic case, in the complex case, we have the following old theorem of Remert. It says that if you consider a complex analytic map that it's proper, then the image of an analytic set under phi is always complex analytic. So in this case, as soon as the map is proper, then it preserves the analyticity of the set. It's the image of an analytic set is itself analytic. In the real case, we would like to mimic what has been done from the algebraic case, where we needed the introduction of semi-algebraic sets to have this Tarski-Seidenberg theorem. And so we may introduce the notion of semi-analytic sets. It has been, I think, defined for the first time by Wojciechowicz in the 60s. And we say that a set is semi-analytic in Rn if it's locally a finite union of sets defined as semi-algebraic sets, but we replace polynomials by analytic functions. So here, the Fi and the Gik are analytic functions. And the definition is locally, because sometimes the analytic functions are just defined locally and not globally, as it's the case for polynomials. Okay. And we ask naturally, is there any result analog of the Tarski-Seidenberg result in the analytic case? And in fact, there is no such a result. So we can see on the following example. It's due to Osgood. It has been more than 1 century ago. We consider the following analytic map from K2 to K3. So here, K denotes either the field of real numbers, either the field of complex numbers. There is no big difference in this example between these two cases. So it's quite elementary. The image of UV is U, UV, U exponential V. And we are interested in the image of phi and in the analytic Zariski closure of the image. So I mean, we consider the image of phi and we consider the smallest analytic subset of K3 that contains the image of phi. And we look at this at the origin of K3. And I claim that this analytic closure of the image of K3 is K3, the image of K2, sorry, it's K3 itself. So the dimension is of the Zariski closure of phi of K2 is 3. The real dimension or complex dimension, depending on the base field. So why is it the case? So to determine the analytic Zariski closure of the image, we need to find all the analytic functions defined locally at the origin, vanishing on the image. So such an analytic function is given by a convergent power series. So I consider such a convergent power series, I denote it by F. And I assume that it's vanishing on the image, so F composed with phi is equal to 0. So in this case, I consider the expansion on F as a sum of Fd of x, y, z, and each Fd is an homogeneous polynomial of degree d. Okay, so now I consider F composed with phi, this is equal to 0. So it's equal to this sum of Fd, where I replace x, y, and z by u, uv, and u exponential v. And because the Fd are homogeneous of degree d, I can factor out u to the d. And I obtain that this sum on the right is equal to 0. So the sum of the u to the d, Fd of 1v exponential v. So because it's 0, it means that the coefficient of u to the d is equal to 0. So each Fd of 1v exponential of v is equal to 0. And because v and exponential of v are algebraically independent over q and over c, in fact, the Fd are 0. And so f is 0. So what this means, it means that the only analytic function defined in the neighborhood of the origin in K3 that vanishes on the image of phi is the 0 function. And so the only analytic set containing the image of K2 on the phi is K3 itself. So we are not in the case as before, come back here, where the dimension of the Zariski closure of the image was equal to the dimension of the image. Here, in fact, you can think about, for instance, K equal to R. So it's R2, and the image of phi under R2 is a surface. In a generic point, it's in fact a smooth manifold and of dimension 2. So its dimension is 2, but the Zariski closure, analytic Zariski closure, is K3, which is R3, which is of dimension 3. So we have the dimension jumps. Okay, so in fact, it works for the real Eden complex, and the problem is that, in fact, this map is not proper. Okay, if I consider this map for the wall R2 or the wall C2, the map is not proper, and there is no contradiction with rematch theorem. But in fact, in the real case, I can take the restriction of phi to the small ball, or the unit ball, or any ball, center at the origin, and in this case, the map is proper. And the ball is semi-algebraic, so it's in particular it's semi-analytic. So it's what I say here. The image of R2 is not semi-analytic at the origin, because if it was the case, if it was semi-analytic, exactly as for semi-algebraic sets, its Zariski closure would have the same dimension as the set itself, and it would be 2 in this case. But here it's 3, because the smallest analytic set containing phi of R2, it's R3. So it's not semi-analytic, and it's neither semi-analytic if I consider only the image of a small ball, any ball, which is compact. I take the closed ball, and the restriction of phi to this ball is proper. So in fact, the result of Remet is not true, is no longer true in the real case. There is really a big difference between the complex and the real case here. Okay, so we need to introduce a new class of subset of Rn that are usually called subanalytic. So we say that the set X in Rn is subanalytic if locally at any point of Rn, X is the proper image of a semi-analytic set. So the proper image under an analytic map. So it's exactly the case of the Osgood example. The image of this R2 or the ball, let's say the ball phi of the image of the ball under phi is not semi-analytic. So we enlarge the class of sets we were considering, take into account this kind of subset of our Rn, and we call all the class of sets we obtain in this way the subanalytic sets. So the name of subanalytic goes back to Hironaka, I think, but in fact they've been studied before, in particular by Gabrielov and also Art and Thom. And this class of subanalytic sets is in fact very nice. It's stable under all the Boolean operations we can make, taking, of course, union intersections, but also the complement, which is less trivial. It's a result of Gabrielov, the beginning of the end even of the 60s. He proved that the complement of a subanalytic set is itself subanalytic. And they're tame in some sense. I don't want to enter into details. Okay. But they're not semi-analytic in general. And the question here is, how far is a subanalytic set from being semi-analytic? So in the example of Osgood, in fact, it's not the image of a ball, the phi is subanalytic. It's not semi-analytic. But in fact, we can prove that it's subanalytic locally at any point outside the origin. So the image of phi, I repeat, it's subanalytic, it's semi-analytic, sorry, everywhere except at the origin. So the origin is the only wild point or difficult point, let's say. And the question in general, what's the difference? And one answer is the following. It's due to Pawłowski. So we consider a subanalytic set in Rn, and I define SA of X to be the set of subanalytic points of X. That means these are the points of the ambient space in which the germ of X at P is semianalytic. So these are the points where locally around this point X is subanalytic. And we have this result of Pawłowski, proved at the end of the 80s, that the complement SA of X and its complement also, both are subanalytic. And this complement is in fact of dimension less than dimension of X minus 2. So it's small compared to X. So it means that in general, a point of X is semi-analytic at a given point, and the set of points where it's not semi-analytic, it's a small set of, let's say, codimension 2. So Pawłowski proved this result in, it's been published in 80. And the goal of this talk is to give some few remarks about a new proof we gave with André Bellotto and Octave Curmi, which is different from Pawłowski's original proof. Which our proof is more algebraic. Pawłowski's result, Pawłowski's strategy was based more on analysis. And my goal is to explain a few indications about this proof, but not all the details because it's a bit technical at some point. Okay, so before giving more details, talking about the proof of this result, I will give new definitions and example. So we talk about ranks of an analytic map. So I work exactly as in the example. I consider the real and the complex case in the same at the same time. So K denotes here the field of real numbers or the field of complex numbers. Both are valid here. So I have an analytic map phi, and I denote by R phi the generic rank of its Jacobian matrix. So, okay, oops. Let's think about the real case. Phi at a generic point. I take phi. I take its image, and its image at generic point is a real manifold. And this generic rank is exactly the dimension of this manifold at a generic point. So here I need to take a small representative, in fact, of phi to be clear, because the image of a germ is not well defined, but I consider a representative of phi defined on some given neighborhood of the origin, small enough, and then I take the image of this small neighborhood of the origin. Okay. This map induces a ring morphism between the rings of convergent power series, which are in fact the germs of analytic functions at the origin of Kn and Kp. And I can consider, sorry, the kernel of this morphism. So the kernel is a set of convergent power series that are vanishing on the image of phi. So this kernel is the zero locus of this kernel is exactly the analytic Zariski closure of the image of phi. So the smallest analytic set containing the image of phi. And the dimension of this analytic Zariski closure is what we call the analytic rank. So RA of phi is the dimension, the crude dimension of this. You can think about the dimension of the analytic Zariski closure of the image of phi. And I can do the same in the formal setting. Instead of considering the ring morphism induced between the rings of convergent power series, I consider the induced ring morphism between the rings of formal power series. And I define the same kind of rank, which is here called the formal rank. And this is this crude dimension. So it's not correct because the meaning is not clear, but you can think about saying something like this formal dimension is the dimension of the smallest formal set containing the image. I mean, the formal set is not well defined, but say we are in a larger class than the analytic one, and we can think at R f of phi in such a dimension. So we always have these inequalities. So the generic rank is less than the formal rank, which is less than the analytic rank. In particular, in fact, we can think about, if you think about the generic rank as the dimension of the image, the topological dimension of the image when we work over the real numbers, of course, it's less than the dimension of the analytic Zariski closure. Okay. Gabrielov gave the following interesting example, showing that, in fact, these three ranks may become different. So we start with Osgood examples that I gave you before. So it induces a map of convergent power series because between the ring of convergent power series in x1, x2, x3, and k of uv, defined in the following way. And I do not give the details here, but Gabrielov remarked that there exists a convergent power series, which is not zero, of course, a non-zero convergent power series whose image under this ring map is there exists a convergent power series which is the image of a divergent formal power series. Okay. What we proved before is that these two maps, phi star and phi star hat, are both injectives. These morphisms are injectives. There is no non-vanishing f whose image is equal to 0. Because it's injective, it means that this convergent series, which is the image of something divergent, it's not the image of a convergent power series. Then Gabrielov defined a new ring morphism, defined in this way. So x1, x2, x3 are sent over u, uv, and u exponential v, as in Osgood example. But the last indeterminate, x4, it's sent over g of uv, this exact convergent power series. So the generic rank of this map is 2, as before. It induces a map between K2 and K4, and we can check that the image is not very difficult. The generic rank of the Jacobian matrix is also 2, as in, for Osgood. Okay, we can prove that this ring morphism psi is injective. So the analytic rank is equal to 4, but the kernel of its completion, so the ring morphism induced between the ring of formal power series, it's not injective. In fact, it's not very difficult to see that it's not injective because this power series is in the kernel, x4 minus s hat of x1, x2, x3. Indeed, x4 is sent over g and s hat also. So it's obviously in this kernel, which is less trivial is to prove that, in fact, the kernel of psi is reduced to 0. So because psi hat is not injective, and this is the kernel, the formal rank is equal to 3. So the formal rank is 3, the generic rank is 2, and the analytic rank is 4. So we have strict inequalities between them, these three ranks. Okay. And just after that, Gabrielov proved the following result that says that maybe these three ranks are different, but if the first two are equal, then the three of them are equal. In fact, if the generic rank is equal to the formal rank, then the formal rank is equal to the analytic rank. A map satisfying this property is called a regular map in the sense of Gabrielov. And yes, the last equality, the fact that the analytic rank and the formal rank are equal, means that the kernel of the ring morphism induced between the ring of formal power series is generated by a convergent power series. In fact, by the kernel of phi star. Okay, with my collaborators, we gave an equivalent form of this theorem, which is quite elementary to state, but it's not that easy to prove. It's the following. If we consider a convergent power series in n+1 variable, x1, xn, y, assume that we may transform f into something which is polynomial in y, but the coefficients are formal power series in x, just by multiplying f by a formal power series. If we can do this in the formal case, then we can do the same in the convergent case. It means that we can find a convergent power series h such that f times h is itself a polynomial in y with coefficients which are convergent in x. So this result is equivalent to the previous result, and it seems easy like this, but in fact it's not that trivial to prove. Gabriel-Frank theorem is quite tricky, and the question was to give a proof, a more general proof of Gabriel-Frank theorem in the sense that we could extend the result. So the idea was the question is, can we extend this result of Gabrielov in a more general and more algebraic setting? This is what we did with André Bellotto and Octave Curmi. So to state my result, I need to introduce a new definition. So we will, sorry, I come back a bit before. So these three ranks are defined here for rings of convergent power series, because we can forget about the original map phi between the ring K between Kp and Kn. We can just consider the ring morphism phi star from the beginning and take its Jacobian matrix and define R phi to be the generic rank of the Jacobian matrix. So I will state a more general rank theorem, but for rings of power series which are different from the ring of convergent power series. So I need to define these rings. So these rings are called Weierstrass temperate families. So we start by we work with our characteristic zero field, which is algebraically closed and uncountable, like C. But in practice, we'll need to consider more general fields. And in fact, I will consider rings of power series, n variables, which are subrings of the ring of formal power series and which satisfy some properties. So you can think about the ring of convergent power series over C, for instance, but in fact, I will consider other kind of families. So the first condition is that these subrings satisfy the Weierstrass division theorem. So this property is a family satisfying this property is called the Weierstrass family. This notion has been introduced by Denef and Lifshitz in the 80s. In fact, we need a bit more than the Weierstrass division theorem. We need some very natural properties like that. For instance, this ring is stable under permutation of the variables, for instance. And we need that this ring is a local ring whose maximal ideal is generated by x1, xn. So this is the first property. The second property we need for a family is the following one. The kind of stability under blowing ups, if you want. We consider a formal power series in n variables, and we assume that if we replace the last variable xn by x1 times xn, it's temperate. It's in this ring, in this subring of power series. Then the original f was itself temperate. It was originally in this subring. So this is a property we need. We need a property of stability under hyperplane sections. So this is the following one. Assume that F is a formal power series which is not temperate. It's not in our family. Then we want that in restriction to a hyperplane, in general, it's not temperate. I mean, the set of lambda in the base field, such that this F, where we consider the restriction to xn equal lambda x1, the set of such lambda for which the restriction is temperate is small, it's at most countable. I recall you that the base field is not countable. So it's quite bigger than this set. And we need another axiom, which is a bit tricky. I don't want to spend time on this, which we call temperateness. It's a bit technical, so you can avoid this to talk about this. Okay, and we prove the following result. If we consider a ring morphism between rings of temperate Weierstrass rings, like this, then we have the analog of Gabriel-Frank theorem. The two if the two first ranks are equal, then the two last ranks are equal. Sorry, I did not define what is RT. It's exactly the analog of the analytic ranks. I come back to the analytic ranks, sorry. It was here. The analytic ranks was the dimension of the ring of convergent power series modulo the kernel of this ring morphism. Then the temperate rank, RT, is the same. It's the dimension of K of the ring of power series we're considering with double brackets like this, modulo the kernel of the ring morphism. And so if the first two are equal, then the last two are equal also. Okay, some examples of Weierstrass temperate families, because I told you that the ring of convergent power series over C is Weierstrass temperate family, but we have other ones. So yes, we have this ring, this family of rings. Again, we have also the family of convergent power series over a non-Archimedean field. For instance, an algebraic closure of the p-adic field. And we have an example which is interesting for us. I will explain why, which we call the Eisenstein series. So it's a bit tricky to explain like this, but you take A to be a unique factorization domain, and you assume that it contains an uncountable characteristic zero field. We do not by L is fraction field, so it's a field of characteristic zero, and it's not uncountable because A itself contains an uncountable field. And we denote by K its algebraic closure, because I recall you that we need K to be algebraically closed. And then I consider this ring of power series. I mean, they're all power series, all formal power series whose coefficients are in some localization of A. You can avoid this C here. It's just a technical C. It's just because we need to work over an algebraically closed field. So we need to replace this capital L by K, but we can avoid talking about K and just think about L. And so in this case, we don't need this C. We just consider the power series whose coefficients are in this localization of A by F. I mean, these are formal power series whose coefficients are element of K, but the denominator appearing in the coefficient needed for the coefficient are essentially all the same. They're powers of F, the same F. Okay, I will explain you later why we need this, but this is an example of a Weierstrass temperate family. Not completely trivial to prove that it's a Weierstrass temperate family, but it is one. And we need to consider, in fact, this rank theorem for this kind of Eisenstein series, to be able to prove Pawłowski result that I gave you before. Okay, and yes, an example of such of Eisenstein's theory, an example of such A. You can consider A to be the the ring of integers, but it's not interesting for us. But there is another example that will be interesting for us is the following. We consider A to be the ring of analytic functions defined in the neighborhood of a polydisk in Cn. So it has been proved by Hsu that it's a unique factorization domain. And we'll consider this Eisenstein series exactly for this ring A. Okay, I come back to the result of Pawłowski. So in fact, the theorem of Pawłowski was a bit more general than what I gave you before. So I need more terminology, more definitions to give you the general statement. I would need to talk about Nash locus of a subanalytic set. So I consider X to be a subanalytic and of pure dimension. So we can define for a subanalytic set the notion of dimension and the notion of equidimensional component. And so we say that it's a pure dimension if it has only one equidimensional part. Okay, in this case, we say that we consider a point P, and we say that X at P is Nash if it's included in a germ of analytic set that it has the same dimension as X. Okay. So roughly speaking, I recall you the example of Osgood, the previous example I gave you before. We had a map from R2 to R3, and the image of this R2 was something of dimension 2, but the smallest germ of analytic set containing this image at the origin was of dimension 3. So the image of Osgood map is not Nash at the origin. That's exactly the situation. And roughly speaking, we can think about a set is Nash when it's the image of a regular map. I mean a map satisfying Gabriel's theorem. That means a map for which the 3 ranks are equal. It's not exactly this in general, but under some condition, it's the same. So in general, for any subanalytic set, not necessarily of pure dimension, we say that X is Nash at a point P if each of its equidimensional part is Nash. So this notion has been introduced by Beersten, Millman, and Schwartz in the 70s. Okay, and I can define the set of points at which X is Nash. So I denote it by n of X. It's a set of points at which the germ X is the germ of a Nash set. And in fact, the result of Pawłowski is more general because it concerns both the set SA of X, of semianalytic points of X, and N of X, the set of Nash points of X. And the theorem says that the complements of both sets are, so both are subanalytic and of small dimension compared to the dimension of X. Okay. A few words about the proof of this, of the strategy of the proof of this result is the following. So first of all, and it was known by Beersten and Millman before, to prove the theorem for SA of X, we just need to prove it for N of X. So I come back here. If we want to prove that both sets are subanalytic of small dimension, we just need to prove it for the complements of the Nash points. It's there is a trick which is a bit technical. I don't want to talk of this, but it was known before Pawłowski result. Then we can assume that X is closed. We can replace X by its closure because, in fact, the closure, the set of points, the Nash points of X are the same as the Nash points of the closure of X. I recall you that.
Sorry, Guillaume.
Yes.
Please, can you back your slide, the previous slide, please, for a minute?
Yes, like this one?
Yes. Okay, thank you.
So what I wanted to say is that we consider here for the Nash points of X all the points of Rn. So it may happen that we can also consider points which are not in X. So if a point is not in the closure of X, it's always a Nash point, and it's always a subanalytic point of X, because the germ is the germ of the empty set. But it may happen that if we consider P to be in the closure of X, but not in X, and in this case, the germ is not empty, even if P is not in X. And it may happen that X is not Nash, neither semi-analytic, at a point of its closure. Okay? So here, the Nash point of X are the Nash point of the closure of X. Because if it's Nash at a point in the closure of X, it's Nash. It's a Nash point of the closure of X. Then, if we consider X as the union of its pure dimension parts, so XD here denotes the pure dimensional part of X of dimension D. So to be Nash means that to be, in fact, each of equidimensional part is Nash. So the Nash points of X are the intersection of the Nash points of each XD. So we can, to prove that this is subanalytic of small dimension, we just need to prove that each of these n, the Nash point of the XD are Nash and of small dimension. Sorry, the complement is Nash of small dimension. So we can assume that it's closed and equidimensional. And in this case, we can use the uniformization theorem due to Hionaka first to obtain a proper map from M to X, where M is a real analytic smooth manifold, and which is proper, generically immersive, and analytic. So that's a black box, let's say. It's a kind of resolution of singularities result. And exactly in this situation, we have what I said before, the set of Nash points, or the set of points where X is not Nash, is exactly the image of the non-regular point of psi. The reg of psi is exactly the points at which the map psi satisfies the equality between the three ranks I defined before. The points where the morphism, the map is regular. And so the set of points of M at which psi is not regular, the image of this set of points is exactly the non-Nash point of X. Okay. And in fact, we deduce the first result of Pawłowski from this second result of Pawłowski. Let's say the following. If we consider an analytic map, so here I come back to the general case, K can be R or C, because I can talk about regular point in the real or in the complex case. I consider an analytic map defined on an open and connected subset of Kp. Then the complement of the set of regular points of psi is a proper analytic subset. So because it's a proper analytic subset, because it's an analytic, its image under a proper map, psi, here, is subanalytic. And this proves that the complement of the Nash point of X is a subanalytic set, which is the most difficult part of the proof. The equality on the dimension is, it was known before, and it's not that difficult to prove. Which is really difficult to prove is the fact that this set is subanalytic. Okay, so that's the strategy of proof we followed, and it's a bit different from the proof of Pawłowski, because this second result of Pawłowski has been proved 2 years later by Pawłowski. The first one was proved in 80, and the second one in 82. And the strategy we use is to use first this second result of Pawłowski to prove the first one. Okay. I did not mean to enter too much in the details of the proof. I can say a few words, but it's a bit technical. Okay, we want to prove that the set of non-regular points is a subset. It's an analytic subset of omega, and it's not omega itself. It's proper. It's smaller. Okay. So the idea is to work in families. So we change a little bit our morphism. We consider a new map from omega times Cp to Cn. So we work in the complex case here. At some point, we need to switch to the complex case. Defined in this way. Okay. So in fact, we can see phi as a family of analytic germ maps. So for each A in omega, we have a germ of analytic map. Okay, I come back to my previous slide. In fact, we can, it's in some sense, we can consider psi, the germ of psi induced at any point A in Kp or Cp, and we consider this family, this set of germs as a family like this. Okay, and so for each A, we have the associated map germ at A, which is in fact psi at the point A. We have a ring morphism induced between the rings of convergent power series. We denote by L the fraction field of the analytic functions on omega. So omega is an open set. We consider all the analytic function on omega, and I denote by L its fraction field. So it's quite algebraic here, but we can consider, so it's a bigger field than the complex numbers, the field of complex numbers, and we can extend the ring morphism from this ring to this ring between the ring of formal power series in x1 xn over L to the ring of formal power series in U1 UP over L. We just consider the map sending the indeterminate x1 xn to their images in the ring of convergent power series in the U1 UP. And we consider this ring of temperate power series. So we consider the union of the ring of formal power series over not exactly the ring of analytic function over omega, but its localization by f. I mean all the analytic function of omega minus f equals 0, in fact. This localization is the set of analytic functions on the complement of f equals 0 in omega. And so we can think about this ring of formal power series over L as formal power series parameterized by analytically on the complement of some hypersurface of omega. Okay, and we have this ring map between the ring of temperate power series induced by phi, like this. Okay, and we can prove that was the third example I gave you of temperate Weierstrass family. These rings are form a temperate Weierstrass temperate family, and so we have the Gabriel-Freund theorem for this. Now we consider a regular point of my original map. So if I take a regular point here of psi, it's a regular point of psi, of phi, sorry. So I take such a regular point. I denote by R the generic rank, and it's equal to the formal rank and the analytic rank at this point, because it's a regular point. After a linear change of coordinates, because the analytic rank is equal to R, I can find n minus R Weierstrass polynomial with respect to the variable x r plus I, which are in the kernel. And the coefficients of these polynomials are power series in x1, xr, whose coefficients are itself analytic in A over some small open subset of omega. They're not defined on all omega, but locally around the point A we considered before. So now we use a result of Pawłowski that we call the extension lemma, and which is based on linear algebra and a result of commutative algebra called Chevalet's lemma on on filtration of local rings. So it was already a result in Pawłowski's paper, original paper. In fact, we can extend this PI as polynomials whose coefficients are analytic, not on omega, on the whole omega, but analytic outside a subanalytic set of omega. Sorry, I'm saying something wrong, sorry. No, we can not extend the coefficient everywhere on omega, but each coefficient can be extended on omega minus analytic hypersurface. But this analytic hypersurface depends on the coefficients. Okay, so the coefficient of P are in L. The denominator may be quite different. And this is where we use the Gabriel-Frank theorem. So we prove, in fact, that if I come back, I do not give the details, but we prove that, in fact, because we have one regular point of phi, we can prove that, in fact, this ring map, phi L, satisfies the Gabriel-Frank theorem. And so these three ranks are equal. And this means that the kernel of phi L contains Weierstrass polynomial, whose coefficients are not only in L, but are analytic outside of one given hypersurface. This is the key point. And so, in fact, these polynomials, Pi, can be extended outside of f equal to 0. And so, outside of f equal to 0, the three ranks are still equal. And so, the complement of f equal to 0 is contained in the regular locus of phi. So this is quite vague, I understand, and I just say that now we can go on in the proof by induction on dimension. Then we restrict or map phi to f equal to 0, and we stratify f equal to 0 into smooth analytic submanifold. And there are several technicalities. It's a bit technical at different points, but this is the idea why we need this Gabriel-Frank theorem in a more general and algebraic setting. So that's it for me. Thank you.